So, as I was saying, so this today is the last class in which we will get back to the radiative processes, and we will expand on a very big topic, which is Comptonization. We will see some of the most relevant aspects. So ideally, you should just I will invite you during this class to just to remember some of the most relevant results that we already obtained when we were talking about Compton scatter, because as you might guess, Comptonization is just everything which is related to Compton scatter in the most general sense. So, as I said, Compton scatter is just the most general description in which you have an exchange of energy and momentum, of course, between a population of electrons and photons. In particular, we saw different cases, different regimes. So, for example, if you consider a photon scattering off a steady electron, who gains energy, who loses energy? Well, in that case, the photon loses energy to a significant amount depending on how energetic is the photon. Because if the photon has a very small amount of energy, well, that's in the Thomson scatter regime. So just the photon just changes direction, but essentially the energy doesn't change. But if you remember the way we treated the problem when we considered Compton scattering, in general, when the electron doesn't move at the beginning, prior to being scattered, it loses, nevertheless, the photon loses some energy. In the Thomson regime, the amount of energy lost by the photon is very, very small, so you can neglect it. So that's why we call the Thomson scattering as a coherent scattering. But to be precise, there is an amount of energy which is lost by the photon. And that's, if you consider the formula that we've come up with when we dealt with the Compton scattering, well, that's the most general case in which you have the electron that doesn't move at the beginning. And in that case, you remember very well that the energy of the photon after the scattering has decreased by a negligible amount in the Thomson scattering case, and no more negligible when the energy of the photon becomes comparable with the rest energy of the electron. But in principle, there is always a loss of energy of the photon for the benefit of the electron. And the opposite case instead instead of having a still electron, you have an ultra-relativistic electron. In that case, who gains energy, who loses energy just is swapped, because in that case, it's the photon which gains energy, increases energy by a factor of gamma square on average at the expense of the electron. So we have these two different opposite regimes. Now we want to study the more general case. So we have a population of photon and a population of electron. And we will see, depending on the average energy of each population, what happens. But we speak in terms of Comptonization whenever Compton scattering is the dominant process which rules the interaction between the population of photons and the population of electrons. Okay, so whenever the regime is such that the spectrum, the resulting spectrum of the photons, is mostly affected by Compton scattering, in that case we speak of in terms of Comptonization. So a Comptonized process, Comptonized spectrum, is a photon spectrum which is mostly affected by Compton scatter. And here I followed some textbooks. The Rybicki-Leitman is one of the most important ones because it carries out many detailed calculations that I'm not going to go through because it takes a while. But just for your reference, just be informed that the Rybicki-Leitman is one of the most important references for Comptonization calculations. And yes, this is, as I said, we speak in terms of Comptonization whenever Compton scattering is the dominant process. And so for other processes, the contribution of other processes that we've seen, such as Bremsstrahlung, for example, can be neglected to some extent. So one can wonder what are the typical cases in which the spectrum is mostly dominated by Comptonization processes rather than, well, the plasma has to fulfill essentially two kind of properties. One, which is a rarefacted plasma. The plasma has to be rarefied. And the second one, and you know very well, for example, think of the Bremsstrahlung. The Bremsstrahlung becomes very effective when you have a very dense plasma. You remember it scales with the number density of ions and electrons. So when these densities are relatively low, it means that correspondingly less important is the Bremsstrahlung. So the plasma has to be rarefied and relatively hot. Because why? Because a hot plasma, it means that the kinetic energy of the electron is sufficiently high so as to ensure a significant amount of energy which is being exchanged during a single collision between photon and electrons. So the examples in which Comptonization is relevant are several. Here I just put some of them. In particular, I am involved in the study of stellar sources, such as X-ray binaries, in which you have one of the two objects, which is a compact object, which can be either a black hole or a neutron star. So there is some accretion. So you have a lot of hot gas surrounding the compact object, and in many cases, the spectrum is indeed affected by a Comptonization. So this is an example, or also as this is an example I was also making about the gas you have in clusters of galaxies. So very hot, and if it's not too dense, you might also see the effect of the Comptonization. Also, the so-called Sunyaev-Zeldovich effect, which is an effect which affects the spectrum of the CMB. And this is typical, this is exactly explained in terms of Comptonization, because you have that the CMB photons just cross the region, which is filled up with very hot and relatively rarefied gas, plasma. So in that case, even if, so you have a gas in which the electrons are much hotter than CMB photons. CMB photons are least energetic. So in that case, they gain energy, and the resulting spectrum, the CMB spectrum, is significantly affected in the shape. And this is due to Comptonization. So you see many examples in which Comptonization takes place and is relevant. So prior to defining that, prior to exploring the details of Comptonization, let's define the so-called Compton Y parameter. What is this? Well, first of all, let's consider the cases in which the photon's energy, as measured in the commuting frame of the electron, is negligible with respect to the rest energy of the electron. So if you remember, this is also the same approximation, the same regime that we consider also in the inverse Compton scattering. So essentially gamma epsilon, if gamma is the Lorentz factor of the electron, gamma epsilon, where epsilon is the photon's energy, has to be negligible with respect to the rest energy of the electron. So this is the regime in which, in the commuting frame of the electron, the scattering is a Thomson scattering. Okay. So in finite media, so what are finite media? Media in which whose size is finite, so not infinite media. We can define a Compton Y parameter. And how is this defined? Well, this is the definition. We call Y, and by definition, it is this first term. This is the average fractional energy change, which is undergone by a generic photon. So if I call epsilon the energy of a photon, delta epsilon is the energy change due to one single collision, one single scattering, and this is just the average. So the average fractional change because it can be either increase or decrease, we will see in a moment, felt by one electron, by one photon, sorry, during one scattering, times what? times the average number of scatterings felt by the photon. So you see, first of all, you see that Compton Y parameter is a number, is dimensionless, because it's a fraction times a number. So you clearly see that essentially is telling you, and of course you see that why it depends on the media you are considering, not only on the single process of scattering between photon and electron, which is the first term here, but the number of scattering also depends on the size of the media, as well as on the optical depth of the media. Okay. So let's consider a thermal distribution of electrons in the non-relativistic regime. So their kinetic energy is negligible with respect to the rest energy of the electron. So you immediately see that in this regime, you cannot apply all what we've seen in the context of inverse Compton. So it's important to have in mind clearly the different assumptions that we consider. So non-relativistic electrons immediately tells you this is nothing to do with inverse Compton. Okay, so let's evaluate the first term, the average fractional energy change. So if I call, using the same notation that we introduced when we first talked about Compton scattering, I called at the time epsilon1 the energy of the photon after scattering. So of course delta epsilon is just epsilon1 minus epsilon. Yes, here should be epsilon, not epsilon prime. Sorry, I apologize for this. I will correct. So what is, well, just use in one case we consider, I didn't say that, we consider two extreme cases. Let's consider first the first case of a stationary electron. So an electron which at the beginning doesn't move significantly. So you in that case, you know that we can apply straight away what we have obtained for the Compton scattering, in which the assumption was exactly that the electron was stationary at the beginning, was steady. In that case, the formula we've come up at that time was this one here. But look, where capital theta is the scattering angle in the in the Laplacian, given that. In this case, let's consider a situation in which photon's energy is much smaller than than the rest energy of the electron, of course. Otherwise, would be a different case. So in that case, what this means is that if you look at the denominator, you have 1 plus something small, because epsilon over mc squared. So it's the, if you remember, is the essentially by Taylor expanding, you see that you have this ratio. So you have epsilon times 1 minus this quantity here. So epsilon minus epsilon 1 minus epsilon, what is that? Well, this is epsilon over mc squared minus, because as I said, due to Taylor expansion, the denominator, this plus becomes minus. And given that here, you see, look at that. We want to have an average value. So, okay, pretty scary. So if we average over all the possible scattering angles, you remember that the Thomson scattering cross-section, not very pleasant. I apologize for the noise. I hope it's going to stop soon. So if you remember the differential cross-section of Thomson scattering, because that's the regime we are dealing with, this is just, this is symmetric with respect to minus to 90 degrees. So it means that when you average over all the possible scattering angles, the cos theta term just cancels out. And you are left with minus epsilon over mc squared, just like that, which is this guy here. And so you see that that's what I was telling you, that even in, if you consider this is exactly the Thomson scattering from one point of view, and you see that indeed the change of energy of the photon is something negligible, because epsilon over mc squared is something very small, and this is a fractional energy change. So the fraction of energy which is lost by the photon, even in the Thomson scattering regime, is very small. That's why on the first approximation that we exploited at the time of Thomson scattering, we just neglected this. But when you want to calculate that, you see that you can estimate how small this is, and that's the answer. This is an average value in the sense that you have averaged out over the possible scattering angles. Okay, so it's no wonder that this guy is negative. Indeed, because the photon has just collided against a stationary electron. So there's no way the photon can gain energy. It's the electron that can gain energy. A very small amount, but this is the how much. Yes, this is something I already said. Let's now consider the opposite, the other extreme case. So the case in which it is the electron which is much more energetic than the photon. In that case, when the two collide, it's the electron which loses energy for the benefit of the photon. How can we calculate that? Well, now we exploit the result that we obtain when we calculated the average energy gain felt by a photon in the inverse Compton scattering. But you immediately say, well, you just said that we cannot exploit what we've seen in the inverse Compton because here we don't have relativistic electron. That's correct. But if you remember the proof that we got at the time, I remind you we obtained 4/3 gamma square energy of the electron. That was the average energy gain. But in that case, we didn't make we just assumed Thomson scattering in the comoving frame of the photon. But other than that, we didn't make any assumption. We didn't require the electron to be necessarily ultra-relativistic. So what this means is that the only assumption here is that we can consider relatively small Lorentz factor of the electron, provided that the electron is still more energetic than the photon, because otherwise there's no way the photon can gain energy. So it means that you can exploit that very result in the limit of gamma, Lorentz factor of the electron, approaching 1. And if you remember that the formula we've come up with was delta epsilon over epsilon average was 4/3 gamma square, beta square, and indeed, in the limit of gamma approaching 1, well, gamma square is just 1, while beta, which is V/C, now counts. Now it does count, because it's no more very close to 1. So this is kind of a trick. We are exploiting the fact that we didn't make any particular assumption. The only assumption of that in that frame was that the electron was energetic enough to give some energy to the photon, or that essentially can hold even in the limit of Lorentz factor approaching 1. Because if you consider a non-relativistic electron, so it's non-relativistic, so its gamma is very close to 1, but still much more energetic than a photon, well, that still applies. So we are exploiting this formula. But in addition, you see, given that we are dealing with thermal population of electrons, you know how to connect the average quadratic velocity of electrons and the temperature of the electron, which I call here TE. So in particular, the average kinetic energy of a non-relativistic population of electron, you know very well from equipartition theorem, this guy is nothing but 3/2 kT. So where TE, I explicitly wrote E by meaning, and I mean here temperature of the electron population, to make sure that one is not confused. Because, for example, if you consider a population of photons, they could also be the result of some thermal process. So they could have their own temperature. So to make sure that there's no confusion, here we mean the electron's temperature, so TE. So you see that here, beta square is nothing but 3 times this guy here. So in particular, 3 kT over m. So if you replace this guy here, you see the 3 and 3 just cancel out, and you're left with this guy here. You see, we are considering, as I said, I emphasize it again, a non-relativistic population of electrons. So this ratio kT over mc squared is much smaller than 1, is negligible. It is a negligible quantity, but it is important. So let's summarize what we've done so far. In one case, so in the case of a stationary electron, it's the energy, it's the photon which gives energy to the electron. And we saw the average fractional energy change undergone by the electron, which is negative in that case, because in that case, the photon loses energy. In the opposite regime, the energy, of course, the energy change is positive, because now considering a population of hot electrons, but still non-relativistic, so the gain, the energy gain felt on average by a fractional energy gain felt by the photon is positive as is this quantity here. Okay, so you see that you have 2 cases. So what's the most general one? Well, the most general one is just the sum of the 2. Just like that. And so here I call NR just to explicitly label this as a non-relativistic case, because that's what we considered. So in particular, if instead of the fractional change, I work out the change, the absolute change of energy, you see that you have this term here. So in particular, it's interesting to consider the different cases, because you see that the sign of the change, so the fact that the photon can either gain or lose energy depends on the sign of this term here among brackets. In particular, when the energy of the photons population equals 4 kT, well, it means that on average, the net energy change felt by the population of photons is 0. So it's an equilibrium situation. In that case, there is no net energy exchange between the 2. Instead, you can immediately see that when the population of electrons is hot enough, and now we know how much has to be, in particular when kT is greater than the photon's energy over 4, in that case, the average energy change is positive. So it means when photons are not energetic enough, are not comparably energetic as the electrons, on average, they will gain energy at the expense of electrons. And this is also very intuitive, if you think for a moment. While in the opposite case, so when the energy, the average energy of the photon is greater than 4 kT, in that case, it means that the population of photons is hotter than the population of electrons. So the energy change felt by, on average, will be negative. So it will be, in that case, the electrons gaining energy at the expense of photons. It's also, now, so far, all this holds holds true as long as we consider non-relativistic, a thermal population, thermal because we are speaking in terms of electrons temperature. So if you speak of temperature, it means that you have in mind a thermal distribution of electrons. Non-relativistic. What happens when we move to consider a relativistic population of electrons? Still thermal. So, well, in that case, what changes is that you no more have a Maxwellian distribution of the velocities. But rather than speaking in terms of velocities, it's more convenient to speak in terms of Lorentz factors. So the distribution in the case of a thermal population of relativistic energy is described by this function here, which to some extent resembles the Maxwellian. If you think that, well, gamma mc square is, of course, the total energy of an electron having a Lorentz factor gamma, and here you have terms which scales as the linear momentum. Gamma mv is also the linear momentum. So anyway, this is just the thermal distribution of a relativistic population of electrons with temperature Te. So the temperature that shows up here again in the exponential term. So in that case, well, what happens? Well, if you have a relativistic population of electrons, you immediately know that who's going to gain energy? It's the photon who's gaining energy. And in particular, now here we can apply the results that we obtain in the inverse Compton treatment, because that's exactly the case. So in particular, you remember very well that we found that the energy gain in the relativistic, so this R here means relativistic case, is on average 4/3 gamma squared. And here gamma squared does make a difference. So it means that when you want to calculate, instead of having a population with all having 1 gamma, you have a thermal population described by this function. It means that when you want to calculate the average energy change, energy gain in this case, felt by the photon, average out over the possible, all the possible Lorentz factor of all the population of electrons, it means that you have to average out also this gamma square. So you have to calculate the average value of gamma square, average over the entire thermal population here. So this is just something for kids. I invite you to carry out. It's just a few integrals by part. And if you work out, you immediately find this result here. So the average value of gamma squared, make sure you can obtain this, you can prove this, is just 12 times this ratio squared. So kT over mc squared. This is the average gamma squared. So if you replace the average gamma squared into this here, what you have is the average energy gain felt by a photon when it's traveling when it's Compton scattering through a population of relativistic electrons having temperature Te. Okay? So you have, of course, 4/3 times 12, 16 times E. And that's the equivalent, the analog result, but now in the case of a still thermal population of electrons, but now relativistic population. What I have in mind is still the Compton Y parameter. If you remember, so far we calculated delta epsilon over epsilon average in both cases, both non-relativistic and relativistic cases. But if you get back to the definition of Compton Y parameter, that was defined times the average number of scatterings. So now let's remind ourselves what the average number of scattering, how it can be expressed as a function of what? Well, from our radiative transfer knowledge, we know that this is just either the optical depth or the optical depth squared, depending on the regime, whether it is optically thin or optically thick. Where tau can be the optical, here I didn't tell you, sorry, ES, the subscript ES stands for electron scattering, okay? So that's what we are considering now. We are considering just scattering between electrons and photons. So that's the only process that is relevant to our purposes. So this is just, if you remember from radiative transfer, this is just sigma n, where n is the number density, or equivalently, if you want to use the opacity, kappa rho. Kappa rho is equivalent to n sigma times what? Well, times the size of the source. So R, capital R, is the size of the source. So this is, and yes, kappa, I remind you, is also the sigma Thomson over the mass of the scattering particle. So in this case, it's defined per unit mass of the scatter. So what is relevant here is the proton mass. And so this is just this guy here, of course, in the case of ionized hydrogen. So let's consider the case in which it's the population of electrons which is much hotter than the population of photons. So it's photons, it's the photon who's going to gain energy at the expense of the electron. So it means that epsilon has to be much smaller than 4 kT. So just to summarize what we've seen so far. So why the Compton parameter? We consider the two possible, we just consider the two cases of non-relativistic case and relativistic case. So the first term is the average fractional energy change. Energy gain in this case, because I already told you, I'm considering the case of electrons much hotter than photons. So you remember that you have two terms in the delta epsilon over epsilon for the non-relativistic case, but given that photons are much less energetic than electrons, you have just only this guy here, times this guy is the average number of scatterings. And in the relativistic case, the only thing that changes is just delta epsilon over epsilon, which is this guy here instead of this guy here. Where this guy here, the optical depth is, due to electron scattering, it's just this guy here. Okay. Things can be a little bit trickier depending on whether absorption can also be relevant. And this can also, you know very well by now that if you consider very low frequencies, at very low frequencies, absorption can, for example, think of Bremsstrahlung, can be relevant. So at sufficiently high frequency, the dominant process can be Compton, so a Comptonized spectrum. But if you then move to very low frequency, then at some point you should expect that absorption comes into play. In that case, things are a little bit more complicated, because in that case, the optical depth is also to include the possible contribution due to absorption. So no more just Compton scattering, but also absorption due to, for example, the process that we will see in a moment. So in that case, you see that the optical depth is no more independent of frequency, but does depend on frequency, in the way that the process for whose absorption it becomes important, it might depend on frequency in general. So in that case, we have to define an optical depth which is a function. So that here at the subscript, I added this comma nu just to express the dependence in this case. And this guy is this guy here. So is rho kappa electron scattering, so the same guy that you have here. Instead of the size of the source, you have an effective length. And this effective length is the displacement that on average a photon will undergo between creation and absorption. Because you cannot just neglect the fact that if absorption comes into play, when finally the photon will be absorbed, it makes no sense just to consider possible further scattering. Well, the photon is gone in that case. So L star, this guy, which I call, this is an L, this is a small L, it's not I. This L star is telling you the average overall path traveled by the photon in the presence of absorption. Well, not just absorption. It can be between creation and absorption, the photon is scattered. But then after being absorbed, it's gone. But in that case, well, I'm here. I'm not going to spend too much time on this, but if the formula that I showed here can be proved as follows. You have both processes at sufficiently low frequency. So both the probability of being absorbed and the probability of just one single scatter. So if you remember what we've seen in radiative transfer, sigma nu here is not the cross-section, is the scattering coefficient, the analog of alpha, which is the absorption coefficient, okay? Remember when we considered the scattering, we added. So overall, what's the relative probability of absorption with respect to all? Well, it's just the corresponding absorption coefficient over the total coefficient. And this is the probability of just of absorption. And so the number of scattering between creation and absorption scales as 1 over the probability of being absorbed. Of course, the smaller the probability of being absorbed, and the higher, the correspondingly higher, the number of scatterings that the photon will undergo between creation and absorption. And so, but the number of scatterings on the other side is what you define as tau squared. Well, tau here I call tau star because it doesn't refer to any specific size, but it's just considering the overall path that on average the photon is expected to travel between birth and death of the photon. So this is tau squared because we are in the regime of a large number of scattering. And so tau squared, well, by definition, tau is the total absorption, the extinction coefficient. So alpha nu plus sigma nu times what? Well, times the length of the path, L squared. So all this guy is squared. But you see, if you invert the relation and you obtain L star, so L star is tau squared, but tau squared is this guy, so the reciprocal of this guy, so this guy here, over this guy squared. Just bringing this on the other side of the equation, and so you get L star, and now finally you can obtain this guy here. Well, you can express, okay, instead of alpha, you can express as kappa rho is exactly the same. And in the end, so when you calculate the effective optical depth, so which takes into account both a contribution of absorption and extinction, so rho kappa electron scattering times what? Times the net path traveled by the photon, which is no more r, but it is this effective length. By replacing, you just calculate. I go pretty fast because these are just a few algebraic passages, and you see you obtain exactly. So this is just a lot, some comments just to provide you proof of the formula that you've got here. This is just to say that on average, as soon as the overall summary comment that I can make on the slide is that on average, as long as absorption can be neglected, and indeed scattering between photons and electrons is the only dominant process, you can just forget about all this stuff, and the Compton parameter just doesn't depend on frequency. This is the case, okay? Instead, when you move to sufficiently low frequency, where typical absorption becomes important, in that case, Compton parameter becomes a function of frequency itself, because you can no more neglect absorption compared with scattering. So in that case, the optical depth is something which depends no more on the size of the source, but on the net path traveled by photons. And so you have a mixture of the opacity due to both electron scattering and absorption, which is the guy which makes the Compton parameter depend depend on frequency, because the dependence on frequency is only on the opacity of absorption, not on electron scattering. And this makes sense if you think scattering between electron and photon does depend on frequency. The cross-section does just depend on frequency only in the Klein-Mishina regime. In that case, yes, the cross-section decreases. But that's a completely different regime. Here, we're not considering this. Okay, we are considering photons which are negligible, whose energy is negligible with respect to the rest energy of electrons. So there's no way. The total cross-section is the Thomson cross-section. There's no dependence on frequency. So that's why kappa electron scattering, it doesn't depend on frequency. Okay. So why is this Compton parameter so important? Well, let's consider a region, a cloud, which is optically thick to electron scattering. And let's consider photons having energy which we call epsilon I, initial energy, epsilon I. And let's consider in particular, again, our population of non-relativistic electrons, a thermal population of non-relativistic electrons. So it means that kinetic energy, kT, is negligible with respect to the rest energy. So kT, much smaller than mc squared, and still electrons that are much hotter than photons. So epsilon E, the initial energy of the photon, is negligible with respect to 4 kT. In that case, well, you know that, of course, based on what we've seen today, energy, photons are going to gain energy. And in particular, let's calculate the Compton parameter. So by definition, the delta epsilon over epsilon on average is this guy here, 4 kT over mc squared. And given that I said that the cloud, the region, is optically thick, well, the number of scatterings is tau squared. Tau squared ES, because that's the only process in which we consider. So in that case, this guy, let's consider that, for example, y is greater than 1. So what happens? Well, let's have a look. If I consider that the energy gain, the average energy gain undergone by a photon is 4 kT over mc squared, well, it means that if I call epsilon f the final energy of the photon on average after one single collision is this guy here. Easy. Well, this guy, 1 plus something small, of course. Well, given that it is 1 plus something small, you can think of it as the Taylor expansion at first order of this function here, of the exponential. The exponential of something small is 1 plus that very guy. So you can iterate the line of reasoning, and you can wonder what happens after n scatterings of this kind. Well, it's equivalent to the product of this guy n times, or equivalently the same here. So the exponential times itself n times, it is equivalent to exponential of n times this guy here. Easy. But in that case, then, if you look at what shows up here as an argument, as the argument of the exponential, is exactly n is the number of scatterings. So is exactly the Compton parameter. So you can immediately see that if you already know the Compton parameter of the cloud, because that's what it depends on. It depends on the energy, the temperature, which tells you about the energy of the electron, the initial energy of the photon, the size, and so the optical depth, and so the number of scatterings of the cloud. You immediately know the Compton parameter. But if you know the Compton parameter, you can calculate the average energy gain. You multiply by E, epsilon E, and you immediately have the average final energy of the photons that cross this region. You see? So that's very powerful quantity, very informative quantity. So if you know the Compton parameter, the exponential of the Compton parameter tells you by how much the initial energy of the photon is increased when the photon crosses that region having that Compton parameter. Provided that what? Provided that the final energy of the electron, of the photon, sorry, is smaller, much smaller than kT. Why? Because, well, in that case, of course, shouldn't this be the case, it means that the final energy of the electron approaches this value here. But in that case, the net energy gain doesn't hold anymore. So, in other words, the photon cannot increase its energy at the expense of the electron indefinitely. When the photon's energy approaches the kinetic energy of the electron, well, in that case, you can immediately see that the energy gain just reduces, just shrinks. So you can also calculate correspondingly by bringing this line of reasoning to the extreme case, you can calculate the so-called critical value for the, for the Compton parameter. And what is this? Well, you know very well that the photon will keep gaining energy as long as its energy is smaller than 4 kT. So you can wonder, what's the critical value of the Compton parameter, which I call Y critical, such that epsilon final will be exactly 4 kT. In that case, you have, beyond that, you have no more energy increase for the photon. So you've just, you calculate the logarithm of both terms, and you divide by epsilon I, and you write explicitly what the Compton parameter is. So the corresponding parameter, which is critical, is now the optical depth. So I call tau critical the optical depth, which corresponds to the critical Compton parameter. So this is just the definition of Compton parameter. And so you see that you immediately obtain the corresponding critical value of the optical depth. So what does this mean? Well, it means that for a given population of photons having an initial energy epsilon I, crossing a region with thermal plasma whose temperature is TE, well, in that case, well, here I just forgot TE. This is a TE also here, TE, both TE. In that case, if the region, the cloud, has an optical depth which is larger than tau critical, well, this formula doesn't hold anymore. And the final energy that photons will have will be just 4 kT. It cannot increase beyond, even if the optical depth is much larger. So, and then the number of scatterings is correspondingly larger. But then the last scatterings do not contribute to increasing further and further the photon's energy, you see? So tau critical tells you, okay, up to this optical depth, photons gain energy. Beyond that, they essentially do not gain any more energy. Of course, this is an asymptotic process. Let's consider now the case of repeated scatterings in two different regimes. In one case, we consider a relativistic population of electrons in optically thin media. And that's what we are going to see right now. So again, let's focus. Now I'm considering a relativistic population of electrons, and the medium now is optically thin. Well, in that case, okay, this is just a comment that I wanted to make, in the sense that something that I didn't prove when we considered the inverse Compton, while the analogous one was, we did it in the case of synchrotron radiation. What is that? When you have a population of Pauli distributed population of relativistic electrons, it can be shown that the resulting spectrum due to inverse Compton is also a Pauli spectrum. This is something that we did in the case of synchrotron emission. We didn't in the case of inverse Compton. Anyway, the essence of that result is that you can come up with a Pauli spectrum of the photons. Here we show another way to end up with a power law spectrum. So the photon's energy distribution is described by a power law, even if the starting population of photons has nothing to do with power laws. Let's see how why. Well, the context is exactly what I just told you. So you need, the recipe is, you need a population of relativistic electrons and a thin, optically thin medium. In that case, well, what happens? Let's call A, capital A, the ratio between the final energy of the photon, final after one scattering, epsilon 1, and the initial energy of the photon. But we know we are in the inverse Compton regime. So you know that on average, this guy is 4/3 gamma, average value of gamma squared. This is a result you see we keep exploiting. But again, I already proved today that this is, for a thermal population of electrons, this is equivalent to 16 times this ratio squared, where T is the temperature of the electron. So it means that after K scatterings, well, the energy gets increased, the energy of the photon gets increased every time by a factor of A. So finally by A to the K, where epsilon I is the initial energy and epsilon K is the energy of the photon after K scatterings. But I remind you, we're considering an optically thin regime. In optically thin regime, the optical depth has the meaning of the probability of undergoing one scattering. So it means that the probability of undergoing K scatterings is tau to the K, because you have tau multiplied by itself K times. Probability of independent K scatterings. So it means that now, if we want to calculate how many photons have gained a given amount of energy, it's equivalent to asking how many photons underwent a given number of scatterings. And I tell you that, well, the intensity that we will measure in the spectrum in the final spectrum of the upscattered photons, so the intensity at epsilon K, will be the intensity that you had at the initial energy of the, times what? Well, times the probability that these photons having initial energy epsilon I underwent K scatterings. So this is tau K, tau to the K. A fraction of them, a fraction of the initial photons having energy epsilon I have been as upscattered to epsilon K. So the corresponding energy due to these photons, now the fraction of that, which is due to tau to the K, now is being now refers to how much energy you have at epsilon K. But this guy you can express as exponential of the logarithm. Well, you can you can do everything of the exponential of the logarithm of something. So tau K is the exponential of the logarithm of tau K, but the logarithm of tau K, of tau to the K, is also K times logarithm of tau. But K, look at here, K can also, A to the K is epsilon K over epsilon I. So if you work out the logarithm of this ratio over logarithm of A is K. So by replacing, instead of K, this guy here, we have this guy here, and exponential of the logarithm of this ratio is this ratio. So this ratio to what? To minus alpha, where alpha is minus logarithm of optical depth over logarithm of A. Is defined with minus minus. Why? Because tau is something which is smaller than 1. So defined this way, alpha is a positive index. So you immediately see that this is a negative. So this is a decrease in power law. And this makes sense, because if you consider harder and harder photons, so more and more progressively more energetic photons, It means that you are considering the luckier and luckier cases in which photons underwent a correspondingly larger number of scatterings. And so it means that you are considering a correspondingly fewer set of photons. If you wonder how many people won once the lottery, you have a number. How many people won twice? A smaller number. How many people won thrice or 3 times? A correspondingly smaller number, and so on. This is a power law. Okay, so you see, in the end, you end up with a kind of power law distribution due to a scattering. So the spectrum of the photons, the initial spectrum of the photon, becomes at high energy a power law distributed spectrum due to the upscattering in an optically thin regime of a relativistic population. And this is one way. The other way is a very complex topic in which, instead of having relativistic electrons, we have non-relativistic electrons. What is this? This is defined by an equation we will see in a moment. So we already saw that in this case, there is a critical optical depth beyond which photons cannot increase any further their energy. And we call that tau critical. And it's interesting also to make an example. For example, if you consider a population of initial photons, for example, with energy 4 electron volt. 4 electron volt is more or less UV photons, I would say. Yes, UV, because 2 electron volts in it's visible. So twice as energetic, it means more or less in the UV. So with a population of hot electrons, so this is 10 keV. So very hot population of electrons, but still non-relativistic, because KT, of course, is negligible with respect to 511 keV, okay? So this is indeed the case. So you can immediately calculate from the formula above the tau critical 11, and the number of scattering, given that tau is much larger than 1, this is just tau squared, so 120. So the Compton parameter in this case is kind of 9. What happens when, so this is just an example in which you can calculate all these quantities. What happens when, so the critical value of the Compton parameter is 9. What happens when the Compton parameter is much larger than 1, and when the optical depth is larger than critical? Well, you see that the population of photons somehow has to reach an equilibrium distribution, because Compton scattering becomes no more effective in keeping on increasing their energy, because you are beyond, the optical depth is beyond the critical value. So it means that in the end, photons will reach an equilibrium distribution. But you know very well, photons are bosons. So equilibrium distribution for a population of bosons, it means that it has to be described by Bose-Einstein distribution. And so Bose-Einstein distribution, in particular, it's characterized, you see that this guy, the occupation number of a Bose-Einstein distribution is this guy here, where alpha, this coefficient alpha, can also be expressed as a function of the so-called chemical potential, mu. And there is a special case. And this case is when the chemical potential is 0. So alpha is 0. And in that case, you see that U nu, here U nu is the energy density associated. But when alpha is 0, you immediately see that you recover the Planck function, so the black body spectrum. When mu is not 0, when the chemical potential is not 0, you are considering a more general equilibrium distribution for the photons. So you can look at the Planck distribution of the black body spectrum as one special case of equilibrium distribution for the photon. But the most general equilibrium distribution for the photons since they are bosons, is this one here where the chemical potential is not necessarily zero. And that's indeed the case in the case of a Compton scattering dominated. What is the chemical potential? Well, I guess you already met this guy, but I'm also confident that when you will be attending the statistical physics course, its statistical meaning will be clarified much more. But just for the time being, a definition from the statistical point of view of chemical potential is that it's telling you if you have a thermodynamic system and you keep a fixed temperature, fixed volume and fixed entropy, the chemical potential tells you the amount of increase of internal energy when you add one single particle. So you have your thermodynamic system, you keep the volume and entropy fixed, you add one single particle to the system. In that case, by doing this, you increase the energy, the internal energy of the system by an amount which is called chemical potential. So that's the statistical definition of mu. As I said, statistical physics will clarify more in detail all this. But if you want, I also added a couple of papers which are telling you more about this, about the explanation of the meaning of the chemical potential. So it means that this is the final, so for a medium whose optical depth is larger than the critical optical depth, and so when the Compton parameter is much larger, it means that the final distribution, the equilibrium distribution that will describe the population of photon, is described by this function here, by the Bose-Einstein distribution function. And you see, depending on the value of alpha, when alpha is 0 is the special case of black body. But otherwise, when alpha is greater than 0, so when the chemical potential is non-zero, it means that somehow the number of the distribution which describes the equilibrium distribution of photons is no more a Planckian function. There's this function here that I show you. It means that there is a mismatch, as I wrote here, between the energy density associated with the photons and the energy density associated with matter. That's no more the case of the black body radiation, in which instead there is a total equilibrium between the population of photons and matter. And in particular, one of the properties of the population of photons which only interact through Compton scattering with the population of electrons is that the number of photons cannot be altered, cannot change, because Compton scattering doesn't change the number of photons. You see, as long as absorption can be neglected, it means that the number of photons will remain constant. And this property is indeed the case whenever the chemical potential is non-zero. There's also a limit, interesting limit, in which when alpha is much greater than 1. So in that case, you see that the spectrum resembles the Wien distribution, so the Wien regime in that case, but with a difference, which is suppressed by a factor of exponential minus alpha. This is indeed, you just take the previous formula, you see that in the limit of alpha much greater than 1, you have this guy here. And here I just showed you some example. I have a few minutes left. I'm not going to prove this. I'm just going to tell you the line of reasoning. Now, if you define the occupation number in the phase space, so let's consider a population of photons. You want to describe the spectrum. It means that you want to describe how many photons that you have per unit volume in one given state. So let's consider the phase space. So the occupation number, which I call n as a function of nu, is how many photons I have in the phase space. So per unit state, per each single state. And if I call u nu, well, in the case of a isotropic distribution, you remember this is something that we already obtained. If I call I the specific intensity and u the energy density associated, there's this relation. This is energy per unit, and energy density, so specific energy density, so energy per unit volume per unit frequency. If you divide the energy density by the energy of a single photon, you have the specific number density. So number of photons, pH is photons, per volume, per Earth, so per. I'm going fast, I apologize for this, but this dN over d nu is the number density of states, which is something that you obtain from standing waves. I'm sure you already did in quantum mechanics. So when you count the number of states in phase space, is equivalent to counting the number of standing waves. That's why I went through K. Overall, I apologize, but so the final relation between the number, the occupation number, and the intensity is this guy here. And the example, one of the example, the easiest example you can think of is when instead of having a generic intensity, you have the black body. But in that case, if you take the black body formula, the Planck formula, you see that the occupation number is exactly this guy. So it is the guy described by the Bose-Einstein distribution in the case of a nil chemical potential, because half alpha and mu here is 0. So indeed, this is the number. The occupation number is telling you, for a given population of with temperature T, the probability of having photons occupying a given energy level, having a given energy frequency nu. Okay, I think that doesn't make sense. Okay, I've just 5 minutes. It doesn't make sense to. I just went too fast. So I just tell you that the general meaning of this guy here. In the end, given that you want to study the spectrum, I'm sorry, because this is a very nice part, but I just go to the final result. This is the so-called Comptonized equation. This is from after a Soviet scientist. This equation essentially describes how the spectrum is affected by Compton scattering, and it is a kind of so-called Boltzmann equation, in the sense that Boltzmann equation is a very general kind of equation which describes how a thermodynamic system evolves when it is far from an equilibrium situation. Very general definition of Boltzmann equation. So the Comptonized, I remember I had a Russian colleague that taught me how to say that. Comptonized equation is an equation which describes how the occupation number of photons in case of Comptonized spectrum changes as a function of, within a given medium. And the final equation is this guy here. Well, the Comptonized equation is this differential equation. When you have the occupation number of photons as a function of what? Well, as a function of y, which is it's not the Compton parameter, but except for a factor of 4 is the Compton parameter, and x is nothing but the photon's energy in units of kT, where T is the temperature of the electron population. And okay, and this describes just the spectrum, the way the spectrum is affected. I apologize, but this, unfortunately, I have to stop. So just to summarize, and then the remaining part of the class is just showing you some special case. Oh, by the way, you can immediately see that indeed the Bose-Einstein distribution is a solution of the Comptonized equation in the regime of because it makes this term vanish, so it is an identity then I showed you some special cases in which of a final spectrum. Here it's an interpretation. So these are just a few examples, and yes, modified black body, saturated Comptonization. So you have the spectrum here, and this part here is the so-called Wien peak, and also unsaturated Comptonization. Okay, I realized that I didn't explain all this part, and let's put this way. I just gave you today the essential elements to start with to go deeper with the Comptonization. Of course, I cannot consider that I have gone through Comptonization. It was not in the original plan to do this. So I'm not, I will, next time, I will tell you what kind of questions I can ask you in the exam concerning the Comptonization. I realize that I didn't explain full. So, sorry, I have to stop here. And